Hello everybody, today I will talk about junction field transistor, junction field effect transistor, which is a device that is similar to the bipolar junction transistor with just different characteristics. So let us see what is this JFET. The JFET is alternative to the PGT, okay, with just different characteristics. The PGT is acting as a current controlled current source. You have a current which is IC, but you control it with the current IB. Okay, you know IC equal beta IB. For the FET, it is voltage controlled current source. So you have a current source, but you control it with voltage. This is the difference. The PGT we have a forward bias base emitter junction. This is how it works. But the FET we have a reverse bias junction that make it work. There are two types of FET. One is called JFET or junction FET, and the other one is metal oxide semiconductor FET or MOSFET. And this is the one that, from the name, it has some metal inside. And there are, of course, usually they have N channel or P channel, or N type and P type. The idea of JFET is similar to this one here. Assume that you have a hose like this and has a water. And what you are doing here is that you have this called the gate, and this gate you are just tidying it. When you tidying it, you decrease the water. That's the idea. When you don't have any pressure here, the water is maximum. But when you start tidying it, in this case, the water will start decrease until you close it completely. This is the idea. It's very simple like this. Here we are talking about the real current, which is the electric current. Okay, so here's the JFET, how it look like. It has N channel. This is a channel which is called which is N doped material. From this side it has a source. From this side it has a drain. This is the terminal here is called a drain and source. And here you have a gate connected to a P-type material, P doped material. And we have a substrate under the channel just for support. That's it. Okay, and this is a symbol for the N channel and P channel JFET. Then how it works? Of course, we know that if we have a PN, for example, this is a diode, you know, PN. Then usually we have around here, around the edge, there's a depletion region. There's a depletion region where the electrons from this side move to the holes in this side, fill the holes in this side, and so on. So we have some depletion region here. Maybe here also we have some here. But the idea is that we need to have electrons moving from the source to the drain, or on the other side we have electric current moving from the drain to the source. Okay, so the current from the drain to the source, or the electron current moving from the source to the drain, depends on how wide this area is. When we have more depletion, of course, this means that the area is narrower. When you have more depletion region, the area is narrower, and this will decrease the current. When you have less depletion region, then we have more area here, then the current will have more current from the electron current from the source to the drain, or electric current from the drain to the source. So here, how we do it, we usually connect the gate to a certain negative voltage. It's called the VGG from the gate. And usually you have this resistor for limiting the current, of course. We add resistor here. And the drain is connected to another source, but it is positive here, and the negative connected to the source. Okay, and we have a resistor to limit the current. So what will happen here? Assume that VGS equals 0. This source is a voltage between the gate and the source. VGS equals 0, which means that this one is 0. There's no voltage here. VGG equals 0. What will happen? That in this case we will have some, since this one is connected to negative will force the electrons to move in the N channel and go to the drain like this. So we have the electrons are moving in this direction here. Okay. So if VGS and VGG are 0, Then increasing VDS, when you increase VDS, the voltage between the drain and the source, by increasing VDD, of course. We increase this one, then we increase the voltage between the drain and the source. What happened that the current, this current here, which is ID, this ID will increase. I drain will increase. Okay, the current in the channel will increase. When you increase the voltage VDD, you increase VDS, and in this case, you increase the current I drain. Okay, so in this case, it will act as a resistor. You know, when you increase the voltage and the current is increasing, this is a resistor. Okay, but when you reach certain point where VDS equal VP, as this VP is equal to, we call it pinch of voltage, then what happened here is that you increase the voltage, but the current does not increase. Similar to the bipolar junction transistor. So here, in the first stage, you increase the voltage, you increase the current. The current and the voltage are increasing simultaneously. So this is exactly as the resistor. But at a certain time, you increase the voltage, but the current is constant. Okay, until you reach a certain point where you have a break off. Okay, so at some point, as I said, when VDS equal VP, or call it pinch off voltage, the current reaches saturation, so it does not increase with VDD, and the device acts as a constant current source. So it doesn't matter what is the voltage, the current is constant. So this is a region, actually, usually when we use it in this region. But if VDS increases more, in this case, what happened? Then there will be breakdown. Okay, so and in this case the current start increasing rapidly. So exactly like the BGT. Until now, it is exactly like the BGT. There is no difference. So let us see here what will happen. Say that the largest current ID happen when VGS equals 0. So this is a curve here when VGS equals 0. This curve. So as I mentioned before, when you increase the voltage, VDS, this is VDS, you increase the current ID. Okay, as you see here. Until you reach a certain voltage where VDS equals this P, pinch of voltage. Then after that, the current will be almost constant. It's almost constant. Until you reach the break of voltage here, then in this case, there will be a breakdown. See. Okay, when you increase VGS, okay, then in this case, or when you increase VGG, when you increase this VGG, the gate source will be reverse biased. Okay, will be reverse biased because it is positive here. See, this one is negative, this one is positive. So this one is negative is connected to positive, and positive is connected to negative. Then it is a reverse bias. So you increase the reverse bias. When you increase the reverse bias, what will happen? That you increase the depletion region. Makes sense. When you increase the reverse bias, you increase the depletion region. And this depletion region depends on what's the value of VGG or VGS. They are related to each other. So when you increase VGG, you increase the depletion region. When you increase it more, you increase it more, and so on. And whenever you increase the depletion region, you decrease the current. This is what happens. So as you see here, when you increase VGG, you increase VGS also, and you increase the depletion region because it is reverse bias. So the current ID will be decreased like this. From here, this is the maximum here. And this one at, for example, VGS equal 0.5, 1, and so on, and so on, and so on. Until you reach a certain point where the depletion region will fill the channel, and in this case, you block the current completely. So here, you increase, you have a certain voltage that will block the current, and you don't have any current. So here, as I said, when VGS increase, the gate source will be reverse biased, causing a depletion region to be more actually, and it will restrict the current ID. So now when you increase this voltage here, this depletion region is increasing, going down, down, down until it blocks this area here. The more VGG, the wider the depletion region until the current becomes zero, and this is what we call it the cutoff. And this will happen when VGS equal VGS off or V breakdown. This one is not P. I'm sorry, this one is not P, I believe. This P is this one here. Okay. So what is the ID versus VGS characteristics? Here it is. So we have three regions, as I mentioned before. The first region where we have the voltage and current are proportional to each other, so it acts as a resistor. We call it here ohmic region. And we have a region here, this is the yellow part here, where we have an almost constant current, and then we have the breakdown at the end. Okay, the relation between the current and the voltage VGS, ID and VGS, is here, shown here, where IDSS, this is a saturation current, so this one here, this is IDSS, and this time 1 minus VGS, of course this is variable, divided by VGS off, this is the voltage, VGS off, here it is, this is the voltage that block completely the current, you don't have any current here. When VGS equal VGS off, then you do not have current, and makes sense here, because if this one equals this one, then you have 1 here. 1 minus 1 is 0, so ID equals 0. Okay, so and all this will be squared. So this is a relation between the drain current or the drain source current and the voltage between the gate and the source. Okay, so this is the equation here for ID. This is the same one. Okay, we can replace this one by having this what we call it here GM. So as a characteristic curves plots, as a characteristic curve plots output current versus the input voltage. The slope of this represents something called transconductance, because it is current versus voltage. And this transconductance is called GM, and it is in Siemens. And the coefficients, this equal to GM0. This part here equal GM0. This part equal GM0. What call it GM0? So this GM equals this value here. So you can write ID in terms of GM and GM0 like this. So it's just a different way to write the equation. But the main part is this one here. But the idea here of GM, because actually when we model the JFET, we model it using this figure here, or this circuit that has this GM. So what is GM? GM is negative 2 IDSS, which is saturation current, divided by VGS off, which is the voltage between the gate and the source, that will make the I drain equal 0. So this GM is 0, and then GM equal GM0 time 1 minus VGS over VGS off. Okay, so if you want to model it like this, then you can calculate GM using these equations here. But this is the main relation for ID. So let's see example. We have this circuit here. All of the examples are so simple for the JFET. Okay, let's see. We have voltage here. This is a drain, 25 volt, and then R drain equals 3.3 kilo ohm. And then we have this is a gate, 220K, and this is VGS or VGG. Sorry, it is negative 2 volt. It's 2 volt, of course. Okay, the negative here is confusing, because actually it's supposed to be 2 volt, but we know that it is negative here, so we're supposed to remove this one here. And it is given that IDSS equal 10 milliampere and IG equal 0. There's no current here. There's no current. IG equals 0. And the VGS off is also given, we need to find ID and VDS. So first, what we need to do is to find ID, and then find VDS. Exactly like when we did with what we did in the bipolar junction transistor. First, we find the IC, and then after that, we find VCE. Here, we find ID, and then later on, find VDS. VDS will be easy, we'll see. Okay, so let us see. This is the equation here. This is the equation. So what is the equation here? Say ID equal IDSS. Here's IDSS. This one here. Time 1 minus VGS. VGS in this case is what? Is the same like, since you don't have current here, you don't have current, then VGS equal what? Equal the same like this voltage here. Because VGS is VG. So VG, between VG and the ground, you do not have current in this one here. Okay, so in this case, between the source is connected to the ground. Okay, so the voltage between the ground and the source is the same like between the ground and the ground here, between G and the ground here. Between G and S is the same like between G and the ground here, which is negative 2 volt. So VGS is negative 2 volt. There it is. VGS off is negative 5. Is given here. That's it. So now we can find ID. We can find ID. Once we get ID, can we find VDS? Where is VDS? VDS is the voltage here between these 2 points here. This is a drain and this is a source. Okay, so you can simply find it from here, or you can find it from here, whatever. It doesn't matter. Here, 25 volt is dropped on this resistor and dropped on this JFET. So this VDS equal what? Equal 25 volt minus ID time 3.3K. Or you can get it from here. VDS equal what? Equal this 25 volt minus ID time 3.3K. That's it. That's it. So this will be, I believe this is the last example here on the JFET.